Hey everyone, so today we're going to talk about introduction to related rates. So after this video, the next video will be about advanced related rates, so we'll talk about a little more challenging of problems. But in a general sense, here are your steps. Okay, we're going to draw a picture if needed. Definitely naming variables, very important, and we use time for t. We also want to write down any other things we find, and the biggest thing is that a rate is a derivative. dx, dt, dy, dt, dA, dt. You're going to see a bunch of these together. So again, derivative is a rate of change. So I think that's the biggest thing you can connect here. So yeah, and then we're going to try to solve for some missing pieces. So take a look here. It says if y is x squared minus 3x, determine the rate of change of y with respect to t. So that would be the rate of change of y with respect to t. dy dt, we want to know what it is at the moment when x is equal to 3, and the rate of change of x with respect to t, dx dt, is 2. Okay, all right, so here's what we got. If you want to write down your given information, we could write it over here. We have dx dt is 2, we have x equals 3, and we don't know what dy dt is. Okay, so we're given this a little equation right here, y equals x squared minus 3x. In a general sense, you can assume that pretty much this entire thing, we're just doing implicit differentiation, which if you guys remember, that's where everybody has that little tag along, dy dt, dy dx, dx dt, all those fun ones. So almost every single situation with related rates, since we're talking about time, every single one is going to be with respect to time. So let me show you what I mean here. So we've got y equals x squared minus 3x. So if I said to differentiate with respect to t, we would have dy dt, that'd be 1 dy dt, right? Then we would have 2x dx dt minus 3 derivative of x dx dt. Okay, so that should make sense for you in terms of implicit that we've done before, but please confirm that you feel okay about that. Again, what you're basically doing is taking the derivative of every variable, but with respect to t. So we need all these little tag-alongs since none of them are t itself. Y's and x's get dy dt, dx dt. So now we can actually solve, since we don't know what dy dt is. We know x is 3. We know dx dt is 2, right here. Minus 3 times 2. That gives me 12 minus 6, which is 6. So final answer. dy dt is 6. Occasionally, and actually I'd say usually, we're going to have units. In this case, it doesn't. So we'll move on to the next one where we're going to talk about area and feet and seconds. So we'll have a little bit more for the units. So it says the area of a square, A, is given by A equals S squared, where S is the side length, T is time. Find dA dt. dA dt. So dA dt would be taking the derivative of A with respect to time. S squared would be 2S ds dt. Okay, so what is dA dt? In a general sense, dA dt, if you read what this is, it's change in area over change in time. So is the rate of change of the area with respect to time. Okay, so that's what dA dt is. Rate of change of the area with respect to time. Each side of the square increases at a constant rate of 3 feet per second. So let's think about what that gives us. The side is increasing. Okay, that's a rate. Side is increasing. So ds dt, the side with respect to time, how it's changing, is 3 feet per second. Okay, when the sides of the square have a length, so when s, the length is 2 feet, what is the rate at which the area is increasing? So what is dA dt? Okay, so see how we kind of picked that apart. And again, related rates, think about what that means. It means we have rates and they're somehow related in an equation. Whoops, I meant to circle this. Derivative slash a rate. We have some variables. We have another rate. So they are related rates in one equation. Here's our given info. The side of the square increases at a rate. So that was why I knew it was ds dt. Then the side was 2, and we're looking for area. So we're going to use this equation right here. So dA dt is 2 times the side length times ds dt. Again, I'm going right off this equation, plugging in this new info we have right here. And 2 times 2 times 3 would be 12. Now this is area, which would be in feet squared per second. So feet squared per second. That's how the area of the square is increasing. Now obviously this would be different if I gave you the rate of change was 4 feet per second, the side lengths were 6. This would be a totally different answer. So it's just at this particular moment in time what's happening. All right, so we're going to try 2 more here. All right, get a little bit tougher. A point is moving on this graph, 4x cubed plus 5x cubed equals xy. When the point is at this moment in time, so this is an xy coordinate, okay, its x coordinate is decreasing at a rate. So x is decreasing at a rate. That would be dx dt. Now decreasing means this is going to be -4. Okay, so look out for that word, decreasing versus increasing. What is the rate of change of the y coordinate? What is the rate of change of the y coordinate at that time? Okay, so again, if you want to write down what we have dx dt is -4, we have x is 1/9, we have y is 1/9, and we don't know what dy dt is. Okay, so that's what we're going to be solving for. There is my equation, so I don't have to come up with one at all. I'm just going to be using it, and I'm going to derive implicitly here, so see what we got. All right, so again, everything with respect to t. So this would bring down the 3, power rule, 12x squared dx dt plus 15y squared dy dt equals, okay, this is x times y. Technically, that would be product rule. So you would have x times the derivative of y plus y times the derivative of x. Okay, so again, take a second, make sure you feel okay about this stage, because what's coming next is we're just going to plug in everything we have. We have x, we have dx dt, we have y, everything except for dy dt, which we have in 2 different spots here. That's fine. We'll just get them together and make sure we can solve for the missing variable. Okay, let's plug in, guys. We've got 12 times 1/9 squared. Dx dt is -4 plus 15 times 1/9 squared. We don't know dy dt. 1/9 times dy dt plus y 1/9 times dx dt. Whew, okay, this has a lot going on. So I'm going to actually simplify it. It's not too bad. It looks a little intimidating with the fractions, but no matter what you need to do is you need to get dy dt by itself. It could be a totally unsimplified fraction if it's for your response. Remember, you don't have to get a simplified answer. So if we multiply these together, 12 times 1/81 times -4, this would be -48/81 plus 15/81 dy dt equals 1/9 dy dt, and this would be -4/9. Okay, so if you notice they all have like 81s and 9s, I found the easiest way to get rid of that kind of quickly here was just multiply by 81. -48 plus 15 dy dt equals 9 dy dt, and this guy would be -36. Okay, and then just get, so dy dt, if I subtract, I would get 6 dy dt on this side. If I add 48, I would get +12. So I divide by 6, and I get dy dt is equal to 2. All right, and that's my final answer here. Again, you could have some huge unsimplified fraction that still simplifies to 2. And we just want to make sure we have our units here. It said units per second, and this is still, y would be units, t would be seconds, so it's not squared or anything. Final answer there, 2 units per second. All right, guys, we're going to try one more here. So take a look. The next one takes a little more background information from geometry, but I believe in you. It says oil is leaking from a sunken tanker and is forming a circular ring whose radius is increasing at a rate. Okay, I'm seeing this increasing at a rate, and I know that's important. Radius is increasing at a rate of 10 meters per minute. So the change of the radius with respect to time, 10 meters per minute. how is the area of the ring changing? So you guys can probably picture this, right? So think there's something leaking out of the boat, there's oil leaking out, and it's kind of expanding in a circle in the ocean. So that's what we're talking about here. What rate is that area expanding if we know the radius is expanding at this rate, 10 meters per minute? So what is dA dt is really what we're wondering. Okay, when the circumference of the ring is 600, so that's very specific. It gives us basically what the radius is. If you guys remember, circumference is 2 pi r. Okay, so 600 equals 2 pi r. So that means radius would just be 600 divided by 2 pi, which is 300 divided by pi. All right, so we've got some info, right? We've got dr dt, we have r, we're missing dA dt. Notice it doesn't give us a formula. So you might be sitting there like, shoot, I was given a formula every time. Now I'm not sure what to do. Think about it this way, guys. Circular ring. We know how to find the area of a circle. We're wondering about an area of a circle. So area is pi r squared. All right, so sometimes there will be some geometry background or a little bit of knowledge in terms of what's happening. I mean, a square, a rectangle, a triangle, a circle. We should know how to find those areas. Okay, so if we differentiate here, dA dt with respect to time, 2 pi r dr dt. Again, I brought down the 2 and multiplied by the derivative of r with respect to time. And I plug in what I've got here. So dA dt is 2 pi r is 300 over pi. And dr dt was increasing by 10, so that was positive 10. And let's see what we get. So that would be 600 pi over pi, which would cancel, times 10 gives me 6,000. Area would be in meters squared. Time was in minutes. So this would be meters squared per minute. So that's how fast the area is increasing of the circle with respect to time. All right, well, that's about it, guys. We're going to try the last two together and see how those go. Please make sure you feel okay about implicit differentiation and the idea of finding the derivatives or those rates coming out of the problem as given information. Let me know if you have any questions, and thanks for watching.